Welcome everyone to this presentation which is titled Safety in Human-Robot Collaborative Manufacturing. My name is Abdullah Al-Hussein. I am a postdoctor from the Royal Institute of Technology in Stockholm, Sweden. And in this presentation, I will talk first about the introduction, and then the safety levels in human-robot shared environment. I will also show a conventional industrial setup where the safety layers are being presented. I will also talk about robotics and the safety regulations regarding that, focused on different aspects regarding the ISO standards that is applied in these kind of cases to calculate important parameters such as the minimum safe distance between the human and the robot, and the robot safe speed, the safety levels for different parts of human body, and also the safety requirements that is currently existing in the robotic work cells. I will also talk about the human-robot collaboration, which is a direction for a new generation of robots, which is more of industrial collaborative robots that nowadays available from different manufacturers. And I will talk first about how this static safety setup has been moved to a dynamic setup instead. And an example that we have here at KTH is an active collision avoidance system, which uses depth sensors as a safety system and defining safety strategies and providing a safety for multiple operators in the shop floor. So first we will try to answer the question which is related to the first point of what is the level of automation that we are that we need in a robotic work cell. As you can see here in the example here, the horizontal level where you have the number of products on each run in the production line, and you have the variant on each run. On the vertical direction, you will have the productivity, which between low and high, and then you have the flexibility in the production line. So basically, if you want to have a low productivity and high flexibility, basically you're talking about a manual manufacturing, where the number of products on each run is low and the number of variant is high. While in the other direction, you have in the right side, you have the far right side, automatic manufacturing, where you have the flexibility is low, the variant in each run is low, but at the same time, the number of products on each run is high. So we are talking about the mass production. So the productivity is high as well. If you want a collaborative environment where human and robot work together, then we are actually talking at the middle approach, where you have the hybrid manufacturing, trying to find the balance between the number of variant on each run sufficient enough, and the number of product in each run is sufficient enough as well. which provide the balance between productivity and flexibility, as we can see in the graph here. In addition to that, there's two main questions that, if we want to go into the direction of collaborative manufacturing, the first one is how to safely protect human in a human robot coexisting environment, how to control the robot and instruct the human during an assembly operation in real time to both avoid collision with the human and fulfill the tasks that is required from the robot. So we can take a look first on the safety levels in human-robot shared environment. As you can see in the graph here, you have the level of importance. And as you can see here, the safety of human actually comes first with the high priority. And the medium priority goes to the safety of the robot itself. And then finally, the low priority on the safety of other equipments that is used in the robotic cell. So these levels of safety can be used as a guidelines in building any collaborative robotic work cell needed in the production line. Currently, if we look at different work cells in any production line in a big company, most of the cases we will see that a conventional industrial setup has been installed. This means that the robot is actually isolated from the human with a surrounding fence. A raw material comes to the robotic working envelope through a conveyor, so the robot will have access to the material. The human will have an interaction region which is controlled by a laser curtain, as you can see in the right side of the graph. And the interaction region is where where the robot can share the same environment with the human. At the same time, this is monitored by the laser curtain. So in case of any interruption, unexpected interruption, the robot work cell will stop in that case. As you can see, the level of collaboration is limited in this kind of setup due to the installation of different layers of safety to fulfill the requirements. And these requirements are basically defined into different ISO standards. More specifically, there are three main safety standards currently used for robotic and collaborative robotic. The first one is ISO 10 to 18, which is two parts actually. The 10 to 18.1 and 10 to 18.2. And these two standards are actually defining the criteria to hand guide the robot using an equipment, and this equipment will be need to be located in the area of the end effector of the robot. And another major criterion, as we can see here, is the movement of the robot. So the robot needs to move in a safe reduced speed, which is less than 250 millimeters per second. and have a safe monitored position. A third aspect is also highlighted in these standards is the robot must sense and keep a safe distance from the human. So in order to achieve that, different sensors need to be installed. The robot need to be monitored, as we will see in the following examples. In addition to that, there's also a recent standard which is at the moment is a technical specification, so it's not a standard yet, which is ISO TS 15066. And this is for the collaborative industrial robotic, which defines different aspects, highlighting the safe speed of the robot and the minimum distance between the human and the robot. So if we look at these standards, we will find different important formulas. The first one is how to determine the minimum safe distance between the human and the robot, which is calculated in the formula shown in the left side of this graph. And you can see here in the example here, the operator is actually trying to approach an area which is within the reachability of the robot. So the question is how the robot need to keep this distance. There's a several parameters, as you can see in the right side. One of them is K, which is the maximum speed in which the human can approach the dangerous region. TS in this case is the total time where the response can happen. TC in this case is the response of the machine itself, the control circuit of the machine, to actually stop the robot in case of human enter into the reachability. And also parameters such as the response time for the safety system, which include sensors installed, if it's laser sensors or laser scanners, where if they are installed in the setup to monitor the environment. If it's vision based, then we are talking about the camera response time. Another parameter is his additional time to actually perform the stopping of the robot itself. So these are this kind of formula is actually defined in the standard with the details on how can be implemented. Another aspect or another another point that need to be taken into consideration is the robot safe speed, which is also defined in the standard, and at different parameters actually define that speed that is needed. The first one is where the area of contact between the robot and the human body, and also the effective mass of the human body part, either it's in a hand or an arm, for example, or the shoulder of the operator, and so on. And also the effective mass of the robot need to be taken into consideration in determining the safe speed, as well as the maximum speed between the robot and the human body in that aspect. So if we look at the different parts of the human body, which is an important factor as well in the determining the level of danger, and as well as the parameters for the safe robot speed. If you look at this example here, we can see that different parts are actually have different levels of danger. Parts like the head of the operator and the arms, or more specifically the hands of the operator, are in a high level of danger, while parts such as the shoulder, the core of the body of the operator is in a lower level of danger. These are basically defined in the standards and based on the statistical analysis of previous cases of accidents that might happen, and studying how the mass of each part of the human body is distributed. So this is also need to be considered in the preparation of a collaborative setup. So if we look at the safety requirements based on the standards, there's a different aspects that need to be taken into consideration. The first level of protection that we can see in a protected conventional robotic work cell is having a barrier fence. So there's two cases of calculating how will be the height of the barrier fence. The first one, if there is a low risk for the operator to be in that hazard region, then the height of the fence need to be around 2.5 meter or more. And if in the other case, if we have a high risk of hazard zone, then the height need to be elevated to 2.7 meters or more to guarantee a safe fence so the operator can work in that environment. There's also different aspects of safety. The other aspect is the entry safeguards. There's different approaches in having an entry to the robotic cell, which actually facilitate in some cases is the interaction between the human and the robot. The first one is the case of interlocking gates. So this can be seen in the production line, where switches can be mounted on the doors and interlocked with a power supply from the work cell. And when the door movement is detected, which in this case someone opened the door, then the switch send an emergency stop signal to the robot, and the whole work cell will shut down. Another approach is to have a safety mat, which is a pressure sensitive, as you can see in the lower part of the the figure in the lower part, where you have the pressure sensitive safety mat, and it can provide a guarding for the entrance of the robot cell. The mat sends a stop signal similar to the interlocking gates to the robot when the operator step on it. And also the mat can be used for both entry region and around the robot as well, if it's needed. Another safety level, or could be also an entry safeguard, is the light curtain. As you can see in the example in the first figure, in the upper figure, where you have the light curtain is actually mounted on the vertical setup, which is used for protecting the operator when the robot is in operation. And they can be turned off when the robot cell is not operating to enable easy access, for example, in the case of maintenance and so on. So basically it works on emitting a safe infrared light beam across the entrance. It sends a stop signal when the beam is interrupted, and the stop signal or the emergency stop signal is sent to the robot and basically shut down the robotic work cell. When it's mounted in the horizontal setup, as you can see in the lower figure, in that case, this is actually useful in case of the need for configuring different safety zones for the robot. And so it can be configured to trigger the emergency stop based on the shape of the object blocking the beam, and also the distance between the human and the robot. So in that horizontal setup, the zones can be defined, as well as having an information about the shape of the object. Therefore, a moving AGV, if it enter to that light curtain, and if they are defined in a way that doesn't interrupt the robot, then it will not trigger emergency stop. While if the human enter to that and block these light curtains, based on the shape, the system can know that the human enter to that loop, therefore it has the highest safety priority. Then it will basically slow down the robot or completely stop the robot as an emergency stop. Another aspect for the safety requirement is the reaching around. This is applied when we have a fence that is lower than the operator height around the robot. And if we have, then in that case, we need to have a distance between the fence itself and the robot working envelope. And basically this gap or this space is defined by the parameter SD in the figure here, where A here in this case is the hazard zone. So in the first example, where we have the movement of the arm is limited only to the shoulder and the armpit. And in the second example, where we have the arm is supported up to the elbow. So in the first upper figure, we have the SD need to be around 850 millimeters or more. and in the lower one could be 550 millimeters or more in that case, which is the safe distance in that figure. So in order to actually have a collaborative environment, the safety requirements that are mentioned in the previous slides sort of create an obstacle to this kind of close collaboration. Therefore, we can see now there is a new paradigm in the industrial robotics using collaborative robots or using an equipment that can be installed to provide this close collaboration with different types of sensors to guarantee a safe interaction between the human and the robot. So if we look at the concept behind the human-robot collaboration, we can see the example here where a robot is actually monitored through different sensors, and the operator can use the voice command to facilitate a collaboration mode, which is in this case hybrid assembly, where the robot is helping the operator to assemble different parts of an engine. The safety system keeps the safe distance between the human and the robot, at the same time trying to follow the operator hand with the safe robot speed. So the end effector of the robot follow the operator hand and hands in the different parts that need to be assembled, so the operator can perform the assembly. So this actually, in that kind of scenario, it's fulfilling the definition for a collaborative human-robot manufacturing environment. So as we can see from the previous example, this is basically moving from the paradigm of having a static safety installation into a dynamic safety installation in that case. As in the conventional robotic cell, where we have the static safety installations, there is no direct collaboration, because it might be possible to define a different zones around the robot to slow down the robot and move away the robot and so on. But this level of collaboration is usually limited, because the system needs to keep a high distance between the human and the robot to avoid any potential collisions. While in the dynamic safety installation, it is actually allow a close collaboration. So this is achieved by the 2 points that is shown here, which the first one is recognizing any possible collisions between the robot and the human, and actively avoid any collision through an online robot control. This kind of setup is dynamically representing the robot with a set of bounding boxes, as we can see in the right figure, the figure in the right side, with different distances, and these distances are actually monitored through the sensors, and controlling the robot according to that, to keep this distance in an accepted level. In this example, the monitor is the robot is actually monitored through the joint values and the CAD module of the robot, while the operator or the human are actually monitored through the depth sensors. And this is how an approach we have developed here at KT Edge that is actually facilitate this kind of collaboration. We have used as a depth sensors, we have used Kinect sensors that is basically capturing the depth information from the scene, determining which are the static parts in the scene, removing these static parts, so it considers that these parts as a background. And then when the human enter into the loop, it will be detected as moving object or as a human with different angles of capturing, which allows us to fuse this information from different Kinect sensors. In this example, you can see 2 Kinect sensors that are connected to 2 mini PCs, and in the local server they are the point cloud are fused together, and the distance between the human and the robot are calculated from the information that comes from the robot controller about the robot joint values, and basically using that to, as you can see in the figure in the left side, where we have these steps of processing, and after that controlling the robot, as you can see in the right side, where we have the signals that comes from the local server all the way to the robot controller, and then all the way to control the robot to avoid collision. So if we look at this, the usage of the depth sensors in the safety system, there's the one that we use, which is the Kinect sensor, is actually working from 0.5 meter all the way to 4.5 meters, which is the region that is detected as acceptable level of accuracy. Of course, it can detect all the way to the end of this graph here, which is 5 meters. But basically, in order to detect the maximum point cloud, which is the full body of the human, taking into consideration that the average height is 1.8 meter, then we are talking about a range between 2.5 meters to 5 meters to detect the full human body. In other applications also, it's possible that we only need the upper part of the human body. Then we can take into consideration the yellow region here in the middle, where we have from 0.5 meter to 2.5 meter. That could be sufficient as a sensing range for the setup of the Kinect. By analyzing these sensing ranges, we were able to decide where to put the sensors in the safety system that we have developed in that case. And we also be able to define a different safety strategies. The first one is to warn the operators. So if the operator is within a certain distance, then it will trigger an audio alarm. And in the second strategy, where to stop the robot if the operator became very close to the robot. And in the third strategy that can be activated, where the robot moves away to avoid collision, if the operator need to actually go there and be very close to the robot. In the fourth strategy, which is actually modifying the trajectory of the robot to avoid collision, which takes into consideration performing a certain task that is needed for the robot, as well as avoiding the collision. So as you can see in the graph here, vector analysis has been used to determine the collision vector and how to avoid it, at the same time fulfill the requirement of the task. So in the example here, the robot need to move in the path which is labeled 2 in the lower part of the figure, but instead it takes the path number 1 because the operator number 1 is in the proximity with the robot. And at the same time, we were investigating how to provide the safety to multiple operators. So in case of having multiple operators in the robotic cell, in this example, we have another operator number 2, standing behind the robot, and to avoid any collision, there's a treasured distance that is defined to keep the robot away from the second operator. And in several cases like this, then stopping the robot could be the action in that case, as you can see in the left side of the figure. So that's basically the presentation that we have regarding the safety in human-robot collaborative manufacturing. Thank you very much for listening.